Okay, so this is the second problem that we did today in class. And again, we're looking at 3D reactions. And when we have 3D reactions, we can sum forces X, sum forces Y, and sum forces Z. We can sum moments about X, we can sum moments about Y, we can sum moments about Z. So we have those three equations. So we have a member is supported by a square rod which fits loosely through a smooth square hole of the attached collar at A and by the roller at B. Determine the XYZ components of the reaction of the supports for the loading shown. Okay, so the first thing we need to do is discern what kind of reactions will develop here at A, and a reaction develops because we don't have translation or we don't have rotation. So I like to just stick my pencil down and just start looking at it. If I were to take this at A, this collar at A, and try to pull it in the X direction, it is on this pole. It is not going anywhere. So I know that I'm going to have a force develop in the X direction. Why is this out of zoom again? Okay, maybe it'll zoom back in. Put the picture here. There we go. Okay. So if I do the same thing, this collar's on this post at Z. If I grab this and try to pull it away, it is not going anywhere because it doesn't have translation. We are developing a force. Okay, I don't know what's going on with this, but it is not staying in focus today. Let's try this. Come on. Okay. So if I try to take this collar at A and slide it up, and it's a smooth square hole, that means we would be able to slide it up without friction. I'm not developing a force. Okay, now let's look at rotation. If I have the x-axis and I push it up at B and try to rotate around the x-axis, it is not going to rotate because that post. So we have developed a moment in the x direction. If I take this system and it's around this post and I try to rotate it around the y-axis, so it'd be around itself, so it'd be like rotating a paper towel holder, it is not going to rotate. And if I don't have rotation, I'm developing a moment. Okay? If I try to push it and rotate around the z-axis, like a clock handle rotate around, it is not going to rotate. And so if there is no rotation, we are developing moments. And we're going to draw them as positive in orientation. So now that I have kind of that figured out, O and at B, it's a roller, so we're always perpendicular. So now I've got to go back and draw my system. And I don't like to draw super tiny systems because I like to be able to see what it is I'm looking at. So I know that we have the x coming out this way, we have the z going up and down. So I have developed a force in the x direction and positive orientation, a moment in the x direction. I've developed a force in the y, a force in the, a moment in the y, and a moment in the z. So because it can slide up and down, we don't develop a force. Then I have B, Z. So that's our force in the Z, okay? I have an applied moment of 50 pound-feet, and if you didn't know that was a moment, check out the units. And then I have this force here that's already broken down in Cartesian vectors. So I'm going to draw it as the components, 20, negative 40, negative 30. So in the x direction, I'm coming out at 20 pounds. In the y direction, I'm working backwards at 40 pounds. And in the z direction, down at 30 pounds. So I'm just going to call them their full magnitude and actually show the direction that we're going. This whole length from here to here is 2 feet, 1 foot, and 2 feet. So I now have all of my unknown forces, my applied loads, my applied moments, and my distances. So we're just going to start at the top. I have 1, 2, 3, 4, 5, 6 unknowns. I'm probably going to need to use all 6 equations. If you don't know where to start, just start with summing forces x. So we're going to sum forces x. We're going to show the direction of positive coming out of the page. And I'm going to start at my reaction and work my way around. So I have AX, come around, and I have 20 pounds plus 20 pounds. It is also coming out of the page equals 0. Do my algebra, AX is negative 20 pounds. I know with 2D, I told you all to give the magnitude, the unit, and the direction. With 3D, you have to assume positive reactions. You have to use right-hand rule. So that if I get a negative 20, we all know it's heading backwards. Okay? Now I'm going to take and I'm going to sum forces. Oh, I forgot to put an X. We're going to sum forces y, which is to the right, is positive. I look at my system and I have an unknown force y. Here at A, I'm going to go around, I'm going to go around, I'm going to go around. Negative 40 pounds. So force y is positive 40 pounds. Let's sum forces z. Up is positive. We don't have an unknown z here because the collar can slide up and down, but we do have bz. Come around, minus 30 pounds equals 0. So bz equals 30 pounds. Okay? We have these unknown moments at our reaction at A. So we will need to use these moment equations. So the moment about the x-axis, I assume positive right-hand rotation. Okay? I'm going to start here. I can develop a moment because I cannot rotate this about the y-axis. So I have indeed a moment about the x-axis. I know I just called it y. I'm in x. Okay? Nothing else here is a moment about the x-axis, nor can it cause a moment. And we're going to walk our way across the page. This is z. If I'm going around the x-axis and I have a clock handle, so here's my clock handle, and I push up on that clock handle, can it rotate about the x-axis? Yes, it can. Is it positive rotation? Yes, it is pushing up and around. So we have plus bz times 2 feet. Okay? We're going to come around. This applied moment is about the z-axis, so it doesn't do anything. X component, parallel to x-axis, parallel forces cannot cause a moment. Let's look at this y component. This y component vector line goes all the way to the left and right, and I can indeed see that it has a distance of 2 feet back up to the x-axis. So if I am at the x-axis and I have this angle and I push it this way, I can see it's going to cause a rotation about the x-axis like that. Positive or negative, that is negative rotation. So I have negative 40 pounds and it is 2 feet below the x-axis. Now let's look at this 30 pounds. Again, about the x-axis. If this angle can rotate around the x-axis and I pull down on it, I'm going to see it's going to cause a rotation. It's going to rotate around, same direction. Minus 30 pounds times, this time the moment arm is 2 plus 1, 3 feet equals 0. So I have mx equals bz negative, because we moved sides, times 2 plus 40 times 2 plus 30 times 3, and bz is 30, so equals negative 30 times 2 plus 40 times 2 plus 30 times 3. So we have negative 60 plus 80 plus 90. So we can find that mx equals 110 pound-feet. Positive in the direction we assumed. Okay, now I'm going to come back. I have an unknown moment about the y-axis, so I'm going to have to sum moments about the y-axis. Okay, right-hand rule, thumb in the direction of the y-axis coming out of the page towards me. That's how I assumed it was positive. Nothing else here is going to cause a moment. This force Z is pushing on it. It would cause translation, but not rotation. This is about the Z-axis, so that's not doing anything. The Y component cannot cause rotation about the Y-axis, but the Z could, the X could. So if I'm now rotating this way, if I pulled on this clock handle towards me, it's going to want to rotate like a clock handle back around. And if we look, oh, my thumb is going negatively, that is going to cause a negative rotation. So I have my minus 20 pounds, and it is 2 feet below, okay? And then let's look at the Z component. The Z component is going straight up, pushing on the Y-axis. So it would cause translation up or down, but it's not going to cause this to rotate. So all of this equals 0. So my equals, take that over, 40 pound-feet. Okay? Now let's look summing moments about the Z-axis. Up, positive, right-hand rule. Means we've wrapped around into the page, back around towards us. Do we have an unknown moment here? Yes, we do. We've assumed it positive. So I have moment Z. None of the rest of these things will cause a moment at Z. Okay, force Z is parallel, so we can't create a moment, but I do have this applied moment at Z, and if thumb goes up positive, wrap around this way positive, I can see this is thumb down, wrap to the back, so we have a negative 50 pound-feet. A common mistake students make is they want to now multiply this by a distance. It is already in the units of pound-feet. It doesn't matter where I apply it in the system, it is causing a negative moment about the Z-axis. So we just leave it pound-feet, okay? Now, if I'm looking at the Z-axis, clearly the Z-force is parallel. The Y-force would run right into the Z-axis, so it would push it, but not cause rotation. But this little X 20 pounds coming out is going to want to wrap right around, wrap around. And if we go back and look at sign convention, if it's coming out, it's going to wrap back around this way. My thumb is going down. So it is actually causing a negative moment about the Z-axis. Okay, a negative moment. So minus 20 pounds. Okay, if it's coming out of the page, and I want to come back to the Z-axis, the perpendicular distance is 3 feet. And all of this has to equal 0. So my moment about Z is a positive 50 pound-feet plus 60 pound-feet. So my moment about Z is 110 pound-feet. Okay? Again, if I wanted to check to make sure that numbers were correct, I could pick another arbitrary axis somewhere, and I could go back and sum moments about any arbitrary point, and I should still come up with the same answers.